Hello, we are going to continue the material, talking about the material that we started in the text on the website. To do that, I have to share my screen, and here we go. And I need the slides so that we can talk about it. And off we go. We had two questions related to the rope around the Earth that was 1 meter longer than the circumference, and we want to investigate the looseness. Looseness 1 was we lift the rope everywhere to the same height so that we create a new circle with a slightly bigger radius, and we discovered that the radius was just under 16 centimeters longer. Okay. To some people that was surprising, but when they thought about it, oh yeah, it was clear. A more difficult problem was if we were to pick up the rope at one point and then pull it tight around the Earth again, and as if we were hanging the Earth on that hook using the rope. And it turned out that the hook would be about 121 meters and 43 centimeters above the surface. How did we do that? Well, we drew a picture. First rule of mathematics, if at all possible, draw a picture. And we gave all the unknown and known things a name, h, the height that we want to calculate, the radius of the Earth, we know that. What we don't know is where the rope detaches from the surface. It will become a tangent line to the circle, so the angle here will be a right angle. Then the distance from that point to the North Pole is needed. And then that distance plus 1/2 of our meter is the length of the rope from the same point A to the hook. And we need the angle in radians for use in the calculations. Well, off we go. What did we do? In 2004, because that's when I wrote the article in Pythagoras, we used that we worked in radians, and so alpha times r is equal to that distance. That is how radians work. Pythagoras' theorem, using this right angle, of course, gives us a formula for h in terms of r, d, and epsilon. And the tangent of alpha is equal to d plus epsilon divided by r, and we can write that as alpha plus epsilon over r. Lovely. That last one gave us an equation that we could solve, or should solve, in order to find what alpha is, then d, and then h. The problem is the equation is hard to solve algebraically, or impossible to solve algebraically or in formula form. So we had to resort to using a numerical solution. Some calculators with a solve button can do it for you, or a computer program, or Wolfram Alpha would do the same with the job for you. And our result was this. Incidentally, we now know how far the point A is from the North Pole, 39 kilometers and a bit. And then the calculator could deal with the formula. We stuck in the d, or alpha times r, if you will, and we found 120 meters and 43 centimeters as the height of the hook. Okay, but I mentioned that in Pythagoras there was also a solution in 1984, and that solution was a bit different. Why? Well, they didn't have handy calculators like I had in 2004. It couldn't solve that equation numerically, so they had to find something else. And the something else was that they found approximations to the tangent and the cosine functions. Now you wonder, where does the cosine enter this story? Well, it enters the story here. We look at the right angle, we look at the triangle again, and the cosine is the line from the center to A divided by the hypotenuse of the triangle, and we can rewrite that equation like so, and we can solve it for h like so. And we get a formula for h that also involves alpha and r, but it looks quite different from that square root thing that we had in 2004. And the reason the authors did this in 1984 was that they could use some knowledge that you normally acquire in the first year at university, but they tried to tell the students, the secondary school students, that you could approximate the tangent or tangent alpha minus alpha by 1/3 of alpha cubed, and the difference of 1 over cosine alpha minus 1, you can approximate that by 1/2 alpha squared. Okay, let's believe those approximations for a moment. We'll get back to them later, but now we're going to use them and see what happens when you take those approximations. Well, then suddenly we can solve the equation tangent alpha minus alpha sort of algebraically. Well, of course, it's an approximate solution, but it's something that we can work with, and it looks quite concrete. And so alpha becomes the cube root of 3 over 2r. And we can stick that into the approximate formula that we get for h, because we get r times that 1 over cosine minus 1, turn that into 1/2 alpha squared, and we get a formula, here it is, for h, an approximate formula, and we'll see, and we can simply put in r and get our result. And here we go. The authors didn't use my value for r. It used a value that they probably got from some table of constants, because it's rounded to the nearest kilometer. And if you take hours, then you will see that it's a little bit different. We'll see that in a moment. Their answer for the height was 121 meters and 50 centimeters. That is 7 centimeters difference. Okay, when you see that, you say, okay, well, 7 centimeters, and we have 121 meters already. Who cares? But as a mathematician, you should be curious as to where does that difference come from? One thing that you should notice is that we use different methods. I use the black box to solve the equation tangent alpha minus alpha, and assumed that the black box gave me more or less the exact solution. And then we put the exact solution into the formula for h. In 1984, the author used approximate formulas and simply said, this is an approximation of h. So it could be that the approximation will give you different answers. The other thing is, we did use different values for r, so that might also be a cause for different results. Here is the difference between our radius and the radius of 1984. It's about 12 kilometers difference. Again, in the grand scheme of things, not very much, but still. Is it the 12 kilometers that explains the 7 centimeters, or is it the rough approximation that suddenly adds 7 centimeters to the answer? We'll see. Well, we can compare our methods. That's no problem. We have our more or less exact solution from 2004, and we have the approximate solution from 1984. We can use the exact quote-unquote method from 2004 to the values from 1984. And what we get is quite close to what the authors in 1984 had. So the approximation from 1984 is quite good, apparently. The same thing happens when we use the 1984 method to and use the value of R from 2004. We had 121 meters, 42 centimeters, and 8 millimeters, and now we get 121 meters, 42 centimeters, and 9.5 millimeters. The difference is, when you look at the further digits, less than a millimeter. So we cannot blame the methods. Apparently, the approximation from 1984 is pretty good, pretty accurate. Then the difference must apparently be in the different values for the radius. And you can see that when you look at the approximate formula that we got, it has R in it. Not just the 1/2, but it also has the R in it, and it has the cube root of R in it. Well, if you take the cube root of both values of R that we had, then you will find, surprisingly, that there is a difference in the cube roots, and the difference is about 12 centimeters. That's quite amazing. You had a really different, rather big difference, 12 kilometers in the radii, but when you take the cube roots, the difference suddenly becomes 12 centimeters. And if you multiply the 12 centimeters by the constant that we have over there, then you do get those 7 centimeters. So who is to blame? Well, the radius of the Earth. Is the radius to blame? No, it's the value of the radius that we used that is to blame. And we will see where those differences come from in a moment. But first I want to tell you where the approximations come from. They come from calculus. This is something that you would learn in your first year at university when you take a calculus course there. Because the instruments that were being used are very important when you want to do calculations with difficult functions. You tend to replace them with easier functions and then see how well your approximate solutions are compared to the real solutions that are really hard to come by. But the authors in 1984 didn't assume that the readers had university educations. They said, well, you can experiment with the tangent and cosine buttons on your calculator to see that, yes, tangent alpha minus alpha is roughly 1/3 alpha cubed, and 1 over cosine alpha minus 1 is roughly 1/2 alpha squared. The other thing you can do, and that would work for pupils in the last year of secondary education, they learned L'Hopital's rule, and then you can actually prove that those limits that you see here are 1/3 and 1/2 respectively, and they will tell you, yes, tangent alpha minus alpha is roughly 1/3 alpha cubed, and the same for the other expression. In 2004, I was able to refer back to another article in Pythagoras where I secretly had calculated those approximations. Well, not secretly, I had been allowed to calculate those approximations. So I had been allowed to talk about Taylor polynomials. And those are the tools that were being used secretly by our people in 1984. Taylor polynomials, and if you follow the pink link here, you will get to the Wikipedia page that will tell you a little bit about them, are used to approximate the functions that we're talking about. When you push a calculator button for the sine of x, chances are that those polynomials are being used to approximate the values of the sine and the cosine and other functions that you want. And once you have I gave the polynomials of the sine and the cosine, and then you can use long division for polynomials to create Taylor polynomials for the tangent function. And so this is what we would call the third order Taylor polynomial of the tangent function. And the difference between that and the tangent function is way smaller than alpha. It's even way smaller than alpha to the fourth. And it's roughly of the order alpha to the fifth. But that's the thing that you would learn in university calculus. And then you can also use long division. And here is a bit here is a small Taylor polynomial for the cosine, and you can divide 1 by that polynomial. And when you do the first step, as you will see, you can try it yourself. You get this as an approximation of 1 over cosine alpha. And you can keep on going, and you will be following in the footsteps of Newton when you do this kind of arithmetic, because that is how he got very many of his results in the beginning of the calculus. He used long division and root extracting and that kind of thing a lot to get things that we now call the Taylor polynomials for the cosine and the sine and other functions. And they're, like I said, they're an important tool because rather than solving complicated equations like tangent alpha minus alpha is equal to something, it's easier to solve 1/3 alpha cubed is equal to something. And so this is what happened in 1984. Now, we keep using epsilon. We don't put the 1/2 in there anymore because we're going to see how h depends on epsilon and r. We had these two approximate equalities, and they are pretty good equalities, as the theory of Taylor polynomials will tell you. And then we solve the first one. Alpha is equal to 3 epsilon over r to the power 1/3. And then we put that into the approximate formula for h. Here we have it. And then we clean it up a little bit, and we see that we get epsilon to the power 2/3 and r to the power 1/3. We already saw r to the power 1/3, but now the epsilon is also visible, and we see that it's epsilon to the power 2/3 that we are using. And so if you were to fix r and write h as a function of epsilon, you will get something that looks a bit like the square root function, but it will be epsilon to the power 2/3. And here, near the origin, you see that epsilon increases very steeply close to 0. So when epsilon gets a little bit larger because of the power 2/3, the h will rise pretty quickly as well. On the other hand, when you look at the cube root of r, we are way out here somewhere. And if my picture was a bit better, you would see that r is really flat. And that accounts for the fact that if we had a difference of 12 kilometers here, and we had a vertical difference of only 12 centimeters here, and that is because we are very far out, and the graph of the cube root function is very, very flat. So over 12 kilometers horizontal, you only rise 12 centimeters vertical. That's the kind of thing that this approximate formula lets you discover. Okay, and so, okay, we did this investigation already, but you can put small values of epsilon and r and large values of r in this formula to see what happens. So for example, if you just take a rope that is 1 centimeter longer, try and find out how high you have to raise the hook to get a taut rope again. You will be surprised, I think, if you try it all by yourself. And there is another thing. So it was the values of the radius and possibly the meter that influenced our outcomes. And yes, the radius of the Earth doesn't really change, but the length is sometimes rounded to make the calculations easier. In a table that I used in school, it was rounded to 6, 4, and then 5 zeros. That made calculations in physics easier. The article from 1984 used a slightly more precise value. And of course, in 2004, I took the original value of the meter and got this as my length of the radius of the Earth. And when you look in Wikipedia, the link is there, you will find that this is the average radius of the Earth, because the Earth is not really a circle. From the side, it looks, okay, I exaggerate a bit, like an ellipse. It's an ellipsoid, and it's a bit thicker, a bit wider at the equator than it is vertically between the poles. And so when you do calculations pretending the Earth is a ball, you take the average radius of that, and that is the number that you see over there. The meter has changed as well. More and more precise measurements in physics made it necessary to change the definition a little bit, and it would also change the length a little bit. It's now defined in terms of the speed of light. You can look that up. And all the changes in measurements and precision and whatnot have now created a meter such that the circumference of the Earth is now not 40 million meters anymore, but 14 million meters plus 7,863. So you can do the calculation from 2004 again to see what happens if you take this length of the circumference, and you will see that the rope goes up a little bit more, a little bit higher than we had, but only a little bit more. You can make the tables yourself. And the polar bear is never in trouble because all the answers are roughly between 121 meters and 40 centimeters or 50 centimeters. That's where the answers are. So the polar bear will not even notice the rope because it's so high up in the air. As a final project, I told you this approximation and also the one for the cosine are pretty good, but they're pretty good only if alpha is small. You can try and investigate on what interval you trust this approximation, whether you want to use it. And the same for the 1 over the cosine minus 1. And then when you decided on that interval, you may want to try for what values of alpha or what values of this quotient, epsilon over r, you are willing to use that approximation of tangent alpha to get to the value of alpha that we were looking for. And then because when alpha is too big, when that quotient is too big, the alpha will be bigger and the calculations will be off. Certainly, if the ball is quite small and you end up with your rope being a little bit like a dunce's cap, so that this angle here is quite big and almost equal to half of pi, and then the tangent is way too big to make our approximation work. So there is a boundary where you can use it and where you cannot. if you do it for the planets in our solar system and for epsilon, add a meter or even 10 meters to the circumference of your planet, then you'll be okay. But if you add way more, then you should be careful. Anyway, that could be a nice project for you to work with. And that is the story of the rope around the Earth and the calculations that you can do with it. I hope you liked it. I'll stop the recording here and we'll see.